Hello and welcome back to Calculus 1. We are finishing up chapter 2. We'll talk about continuity today. So continuity in some broad strokes is explained through the graph in terms of if you can draw a graph in one continuous stroke, we can call it continuous. So that's not all of the story, obviously, but it's a good start point. So if you are able to draw a function f of x without lifting a pen, it fits the definition. If you look at a graph that it's interrupted, right, you have to lift the pen and then go draw somewhere else. So let's say ends here and then picks up there and goes on. Let's call this one g of x, for instance. We would say f of x is continuous and g of x is discontinuous. But there are other ways to be discontinuous. And if you study calculus, pass, right, just Calc 1, 2, and 3. If you take advanced calculus, you will learn about functions that are continuous, but you actually have to draw those in segments. So those exist as well. But you know what, it's a good thing to start here. So continuous, not continuous. Now please note that continuity over here was broken at the single point A, right? X equals A. So the function is actually continuous everywhere else except at that one point. So we start defining continuity at the point, and then we go on to global continuity, and then we talk about discontinuity, and then we talk about piecewise continuity, and we all go home right after 2.7. So let's start with continuity at the point. So f of x is continuous on x equals a if, and now we have these three rules. Rule number one is that f of a must exist. Number two, limit of f of x as x goes to a must exist. And number three, limit of f of x as x goes to a has to be equal to f of a. So these are your three rules that you have to check to determine if the function is continuous at a single point, at the point A. Now, before I go do any examples, I'm going to talk about notation, because if I put on the test, state the rules of continuity at the point, you are supposed to write these three. And in the past, I've seen some horrific things like limit of f of a must exist. Limit of f of a exists all the time because f of a is a number, it's not a function. So, right? So silly stuff like that. So we have to make sure that we understand what's what. X is a variable. Can take on any number. X equals a is a number. Example would be x equals 3. Okay? That's an example. When I say f of x, I mean function. Y equals f of x. When I say f of a, well, that's a number. Because y equals f of a, which could be, let's say, f of 3, and maybe the answer is 8, or whatever. So f of a and f of x is not the same thing. F of a, when I write f of a, we see a number in there. When I write f of x, it's a function, and they behave differently when you start plugging them around. So the limit of f of x is going to be some number L, or infinity. The limit of f of a, which is what we never do, is just f of a, because limit of 3 is 3. That's technically how silly the whole thing, and this x can go anywhere. I'll put 100, doesn't matter. So there is a big difference between f of a and f of x. There is a big difference between x equals a, which is a number, and just x. So when you toss in this a, that means you are talking about specific value, and your calculation is already a constant in there. So that a is a 3 or whatever, you're regarding all of that as a constant all the time. And if you have f of x, then it's a function, and you have to be careful, and you have to use all of the rules for that. So now, technically this one over here says y value exists, y answer exists. So pre-Calculus1 works. You can calculate that value. So whatever wording you need for the first rule is simply you are calculating using pre-Calc1, you are calculating e squared or sine of pi over 3 or x squared, right? So 3 squared plus 7. You are calculating the actual value using pre-calc. The second one is obviously our chapter 2 limit, and the third one just says 1 is the same as 2. So you have the same number that you obtained from 1 and 2 is number 3. So that's what we have to understand our 3 rules, which we are going to use to see if the function is continuous. So let's take a look at an example. Is f of x equals x squared minus 9 continuous at x equals to 5? So now this 5 is your a. That's your a. You remember it's x equals to a? So your a is 5. All right, 3 rules. Number 1, f of a must exist. That means that you have to calculate f of 5, which is 5 squared minus 9, which is 25 minus 9, which is equal to 16, exists. Great. Gets the green check mark. What happened to my green? Orange, out. Give me green. Boom. Next one. Number 2. Limit x goes to a of f of x must exist. Well, limit x goes to our a is 5 of x squared minus 9, and now this worked out to be, remember that we said in 2.3, if there are no zeros in denominator or anything weird happening, you are allowed just to plug in. So this is going to be, again, 25 minus 9, 16. So it exists. Yay. And finally, number 3 says that number 1 has to be the same as number 2. Well, 16 equals 16, that checks out. So, since all 3 rules hold, f of x equal x squared minus 9 is continuous at x equals 5. So we did all of this work just to prove that this function is continuous at the single x value, x equals 5. We don't know anything about x equals 4 or negative 1 or 10. We only know that this is continuous at 5. What are you going to do if we actually want to know what's happening at 10? You got to do this from scratch. And then someone says, how about negative 3? Do it from scratch. How about 100? Do it from scratch, right? How many points are there to check? Infinitely many, right? So we would have to do infinitely many of these to check for each single point, which is a little bit, right, tougher to do. Who's the only person that can count to infinity? Oh. It's obvious.
Decimals.
I said who, not what.
Oh.
It's probably the person you're thinking of is just not saying. Come on. No.
That's what I was thinking.
I said count to infinity. So you have to be realistic. Come on. It's the same person that when he does push-ups, he's not pushing himself off the edge, he's pushing Earth away. Chuck Norris, there we go. Nice. Yes, Chuck Norris is the only one who can count to infinity. Twice in 5 minutes. Okay, so it was obvious. It was obvious. He's also the only one who can divide by 0 too. So, yeah. For you, you will have to actually calculate the limits and stuff, right? Until you get to these levels, and then you can claim stuff. Anyway, all right, we're good that we clear that, because the next example here is going to take a look at a piecewise function, f of x, that it's given to us as 3 for all x's smaller than 1, and it's given as 2x minus 3 for all x's larger or equal than 1. And we want to know if this is continuous at x equals to 1. Right? So that's what we want to know. Well, it shouldn't be that difficult to compute this, right? We start with number 1, and we ask ourselves, does f of 1 exist? Well, where is the line that computes at 1? It's this one that has x equals, right? So our f of 1 is equal to 2 times 1 minus 3, which is equal to 2 minus 3, which is negative 1. We put a green check mark. It passed the first rule, because we are able to use pre-calculus to compute 1. Now, be very careful, guys. The reason why we are able to compute this here is because there is an equal sign. That's x equals 1. It belongs here. X equals 1 belongs here, because that's what x equals to 1 is. If there was no equal sign here, it was just larger than, then it would not belong there, and it would fail. So luckily, we had the equal sign, so that was the line, that was the function, right? The line at which we calculated the function. Number 2, the limit as x goes to 1 of f of x. Does it exist? Well, we see that there are 2 different functions, one from the left and one from the right, so we have to use the one-sided limits from before. Remember the Romeo and Juliet? We used the red one for the left approach, and then the blue one for the right, for Romeo, right? So as we approach Juliet over here, x1 minus, we have to use the top function, and that's 3. Because it's always 3, no matter what you pick, right? So we pick 0.1, 0.9, 0.99, 0. Right? They're all going to be 3, because it's just a constant coming into that. And the Romeo on the other side, blue, limit x approaches 1 plus, well, he's going to write 2x minus 3, because that's from the other side. Right? The values that are bigger than 1 are here. And this is bigger than 1. This is 1 plus. You are approaching from the right. So Romeo is going to use that. So you plug in 1 and you get -1. Whoo. What did we just see over here? Limit x goes to 1 of f of x. What? Does not exist. Very good. Because the left limit and the right limit do not agree. That was the first major theorem we learned in calculus. The left limit and the right limit must have the same value in order for overall limit to have the same value. That was the way to calculate limits. And point number 2 fails. Clearly, we're not going to go and calculate anything for 3. We'll just say f of x is not continuous at x equals 1. And you move on with your life because you're done. Right? So all 3 rules, you have to learn this, obviously. You have to learn these 3 rules. And if all 3 rules hold, it's continuous at the point. If any of the 3 fail, it's not continuous, and that's the end of the story.
Don't you really only have to check 1 and 2 though? Because if they check that, then
you have to also do number 3 because they have to be the same. So here is why. Now we're talking, which is great. You are asking that question, which is immediately the next thing that we have to talk about. So, woohoo! I'm going to draw 3 graphs over here for 3 possible ways to fail. One of which is not doing homework, one of which is not doing labs, one of which, the continuity. Yes. All right, so I'll place these guys, and then you. So these are the 3 cases, and as soon as one of them checks out, you don't have to keep checking, right? It's out. Now we clearly see that all 3 are discontinuous. We can fail 1, 2, or 3. We can fail 1, 2, or 3. We can fail 1, 2, or 3. Remember that number 1 is f of a exists. Number 2 is that the limit of f of x exists. And number 3, limit x goes to a of f of x is f of a, essentially saying 1 is the same as 2. So these are the 3 rules, and in this order, 1, 2, 3. So now, tell me for the first one, what fails on the first one? We start with f of a. Do we have f of a? Where is it? Where is the f of a on that first graph? The black dot. Very good. So it passes the first because it's right here. So this value f of a exists. The black dot is the f of a value. That point is a f of a. Oh, no. Panic. So this point over here, because this is where your a is, this is your a f of a, clearly exists. That black dot is that. So that's good. Okay, so now, second one. Does the limit exist?
yes.
I heard no and yes. What, we're going to take it outside now? It's kind of close, though. No? We're going to be a civil way to decide if the limit exists? It does not. Why? It's different from left and right. Very good. As Juliet approaches from the left, she is going to end up on the f of a level. As Romeo approaches from the right, he is over here on top of the hill. They don't meet at the same location. So the second rule over here fails. Limit does not exist. This is one that we would call jump discontinuity. Jump discontinuity. as the limit fails to exist. How about the next one? Do we have f of a? Yes, we do. The black dot. So that will be f of a, right? Check. Do we have limit? Yes, we do, right? Because you approach from the left, you approach from the right. They end up on the same height. So that's a check for this. So now we have that L is up there and f of a is down there. Are they the same value? Clearly not, right? One is higher than the other. Therefore, with the smile, we say X on this one, right? And this is what you asked, right? This is exactly what you asked. Why do we check number 3? Well, here is the case where 1 and 2 passed. Function value exists, limit exists, but they're not the same value. So you have to check number 3, because number 3 makes sure that they're the same. This is the way. This is the one that I use the analogy of a collapsed section of a bridge. Bridge is not continuous, right? If it collapsed in the middle, they can what? They can just charge half a fare because half of the bridge works. Makes sense? Yeah. That would be kind of good, right? Verzano is like $20, so it's like $10. It's a bargain. The problem is that, like, 200 feet of that's missing in the middle, but, if you drive fast enough, I mean, you might make it to the other end. We don't know. Next one. What fails on the third one? First immediately fails. Because there's no f of a. There's no black dot anywhere, right? It's just a hole. So this a value will just shoot straight through and will never bounce into the y-axis, because the f of a is determined when the function hits when the vertical line hits the function and reflects in the y-axis. It's just going to go straight through the hole and never bounce off. So it fails on the first. We don't even get to check 2 and 3 because there is no f of a. It's nothing for us to do anymore. So these are the 3 ways in which it can fail. And we have seen one of these ways here, which was with this piecewise function, the limit failed, right? The second one. So that was our first picture. So that piecewise function would graph something. Well, I mean, we can graph exactly what that. We had f of x was 3 for x less than 1. And 2x something, 2x minus 3, for x bigger or equal than 1. So if you want to graph this, you put this is not an asymptote, this is just a barrier for me to draw the graph. I have 3, so 1, 2, 3 coming in, all the way to 1 with the open circle. And then I go at -3. I go 2 units up, 1 unit over. 2 units up, 1 unit over. 2 units up, 1 unit over. It will look like that forever. That way, forever that way. And now I can remove my construction lines. Label this as 1. Clearly discontinuous when you look at it, right? And the issue was that our function was the limit, wasn't it? Right? The left limit. And you also see your f of a was, if you remember, your f of 1 was -1. You can clearly see it on the graph. It's -1. So it all works out perfect. So now we should talk about global continuity. We said that we use these 3 rules to check continuity at the single point. But then, what about other points, right? It's like, you have more than one child, you pick your favorite, and that's the one that gets to enjoy life. The rest is like, right? Do we have any like a third kid in a family. Like no one even looks at you, right? That's how it is. Anyway, what? Too close to home? Okay, good. It's the middle one that it's always right. Anyway, so global continuity. Function f of x is globally continuous if it is continuous at every point in its domain. That's a lot of points to check, right? A lot. Luckily, we have theorems. And you learn the theorems, and you can do the problems. You don't learn the theorems, you are doomed in calculus. So, a major theorem states following functions are globally continuous on their domains. Number one, polynomial. Polynomials. P of x is equal to a0 plus a1x plus a2x squared plus dot 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 plus an x to the n. This covers a lot. Your constant function, y equals to 5, right? Your linear functions, mx plus b, your quadratic, and then cubic, and then whatever other power. So it covers a lot under polynomial. Number two, exponential. Y equals, let's go with b to the n. Could be e to the x, 2 to the x, 1/2 to the x. Could be any of those. All the negative decay, all of them. 3. Logarithmic function. Y equals log base b of x. I don't know why I use then. I'm going to change this b to the x. I changed here to b to the x to be consistent where x is independent variable. So log function. Log function is continuous. Number 4, sine x and cosine x. You see, from negative infinity to positive infinity, they're continuous everywhere. Tangent has the vertical asymptote, has infinitely many vertical asymptotes, right? For tangent. You have at pi over 2, 3 pi over 2, every pi over 2, and the negative ones. Cotangent, cosecant, and secant, they all have. So all 4 of those have infinitely many vertical asymptotes. They're not continuous, right? They will be piecewise continuous, but let's get there, right? So we have globally continuous function. Remember, you draw the entire function from negative infinity to positive infinity, or for your, let's say, a square root or your log from 0 to infinity, you draw just all of the lines that exist. You draw just one stroke, no asymptotes anywhere, right? Those are, right. So now we have radical functions, like square root of x, cube root of x, fourth root of x, and so on. I should just say nth root of x as a radical function. It has all of those. So these are your globally continuous functions. And when you're solving the problem, you don't get to sit there and calculate infinitely many points to prove that 3x plus 7 is continuous. You call on this theorem, because this theorem is already a result that is prepackaged for you to use. Sounds good? It's just global continuity of functions, the list of globally continuous functions, right? So it's a list of everything that is globally continuous that you learned so far. There are hyperbolic functions coming up in Calc 2, so you will learn more things as you explore mathematics and your engineering. You will add. List is never finite, right? The trick is that these are the ones that we are going to use in Calc 1 and Calc 2. And I will show you where this thing fits. So this is the thing that you're learning now, so that you're not just passing Calc 1, but also Calc 2. And I'll show exactly where this fits. But before I do that, theorem with a vengeance. Combinations and composition of continuous functions are continuous. Combinations and compositions of continuous functions are continuous. This means f plus g, f minus g, f times g, f divided by g if g is not 0, constant times a function, f raised to a function, nth root of the function, and finally f composed to g or g composed with f. So all of these now would be continuous. We can take a look at a quick example. Say your f of x is x squared minus 3x plus 8, and your g of x is 2x minus 1. Now when you look at this, f plus g will be continuous, because you have x squared minus 3x plus 8 plus 2x minus 1 for a total of x squared minus x plus 7. That's a polynomial. See that? So you are going to, so what is your proof here? You would write a paragraph that will state, so proof, f and g are globally continuous. This is you calling on the first blue theorem, because they're both polynomials. You can write that because they are both polynomials. So this is you calling on that. And then you say, then you are calling on the second blue theorem, saying combinations of continuous functions are continuous function. Done. That's all it is. So you call on the first theorem because both f and g belong to the list already. And then the second theorem says that if you add two of them, you are going to have this situation. Problems like this you're going to see in Calculus 2. See, Calculus 2 is not hard in terms of a concept. Calculus 2 is a living nightmare if you don't remember your trig and your Calc 1. So, you know, technically, like Calc 1 C grade, barely past Calc 1 is pretty much, there's no way. Calc 2 is like, don't even bother signing up. Like, that's pretty much what it is. Now, I do have examples of Calc 2. And immediately, because I show this all the time, it immediately opens on a section where you have. So here I have a function, f of x is 1 over x squared on interval 2 to infinity. Is that continuous? Yes, because 1 and x squared are continuous. Calling on that first, they are both polynomials. 1 is a constant and x squared is a polynomial, right? They're all polynomials. And their quotient is continuous because denominator cannot be 0. Denominator cannot be 0 because 0 is excluded. If you take a look, a domain is 2 to infinity, so it's not 0 ever. So I'm calling on quotient of two continuous functions is continuous if denominator is not 0. That's the proof. You also have to prove that it's positive and decreasing, and then you can do the problem. Welcome to Calc 2, right? So if you can do continuity, then the problem is done. Here is another example. Use the graph on that one. We know what 1 over x looks like, and I just drew where the 1 is because we are 1 to infinity. That's the piecewise continuity. We'll get there. Do I have more? P-series. Great. Another composite function, 1 over square root of x plus 8 on 0 to infinity. Square root of 1.8, x equals negative 1. Negative 1 is negative 8. So negative 8 would be a problematic point, right, to create denominator equal to 0. If we go back to our theorem says division is continuous if denominator is not 0. So now, all I need to show in this Calc 2 class is the denominator is not 0, because I have two polynomial functions that are continuous. I have a function composition, square root is continuous. So everything is continuous as long as this can't be 0. So I calculated that it would be 0 if x is allowed to be negative 8, but x is not allowed to be negative 8 because negative 8 doesn't belong here. Therefore, not in that. Yes, it is continuous on 0 to negative infinity. If you go from negative infinity to positive infinity, it will be discontinuous because it will fail at negative 8. However, since we are only chopped here at 0 to infinity, then the problem point is not included. Therefore, it's all good and it's continuous for the piece that we need. So this kind of stuff, this kind of proofs, and these theorems, these two blue theorems that we covered, the list of all functions and the way they combine, that's coming up in your Calc 2, it's coming up in your Calc 3, it's coming up in your differential equations, right? Obviously, if you're not taking any of those courses, right, make sure you do this one problem on your next exam and you're done, right? But I know, right? But if you are going on, this is it, these two theorems. You must know them, otherwise you are doomed. With like 6 O's. Doomed. And the last part that I want to talk about is that notion of the piecewise continuity, which is actually all of this Calc 2 stuff that you just seen. It's actually that because we had the chopped domains, right? So, piecewise continuity. And one of my favorites over here would be 1 over x, obviously. So y equals 1 over x. We immediately know that it's not continuous, right? So we write that in blood. Globally, not continuous. You can write because x equal to 0, no limit. So number 2 fails, right? At that point. Well, number 1 fails as well. There's no function value at all, so they all fail. But if you take a look at the graph, you see 2 perfectly continuous pieces. So we don't get to throw this function to garbage because it's discontinuous at this one point. You have seen me use it in 2 different examples in Calc 2 where this situation, because sometimes all you need is a domain that is, let's say, positive values. Well, 1 over x is perfectly continuous for positive values. It's not good for 0, but it's good for positive. It's good for negative values as well. But in most cases, later on, right? Because the time starts at 0 when you start measuring, and then it moves on with the positive values. Your x-axis most of the time will be actually a t value, time, right? Elapsed time. You want to talk about physics, differential equations. Your x-axis is always t-axis, and t-axis is positive time. So you are going to pick your initial state where everything starts, right? We can go as far back as Big Bang. Do we care what happens at the Big Bang? No. Do we care what happens before Big Bang? Hell no. Because why would you? There is no reason. What's south of a south pole? Right? The question doesn't even make sense. The question doesn't even make sense. If you have a planet and you have a south pole, can you go and break your head what's south of South Pole? Right? No, you don't. Because when you're at the South Pole, the only way you can go is north. When you're at the North Pole, the only way you can go is south. Right? And that's it. You don't even talk about left, right, anything. When you're at that point, you can only go south from that point. When you're at the equator, you can go left, right, and you can go anywhere, right? You have infinitely many directions to go from that point. But when you're at the south point, you can only go up. So now, thinking about this, in certain cases, you can only start at a certain point and then go from that point on. Another example, cake. When do you start talking about the cake? When you obtain the cake. Either you made it and now you have it, or you bought it and now you have it. Is there a negative time for a cake? No, there is no negative time for a cake. Right? The existence of cake is at the moment that you obtained it, and you can just enjoy it from that point on. So t is positive. So it would make sense that for certain application, you are only going to take a look at, let's say, only positive side of the graph. So now I get to say in green, 1 over x is continuous on 0 to infinity. It's perfectly continuous. And that's what we call piecewise continuity. You can talk about another one, which would be tangent graph. Negative pi over 2 asymptotes. Is tangent continuous? No. It has infinitely many asymptotes. Therefore, it's chopped up as it can be. Now, do we have pieces that we can actually use as continuous and model the change in temperature or whatever? Yes, right? So, tangent x is globally discontinuous. And then now in green, tangent x is continuous on negative pi over 2 to pi over 2. We call that principal period. So for this period pi, you have this, and you will use that one to create inverse trig function. See, I even see that not a lot of people actually go into that detail to make the distinguish between inverse and inverse function. That's not the same thing. Inverse and inverse function are not the same thing. Anything you draw has an inverse. But is everything that you get a function? No, right? So if you think about that, if you have this tangent that does this forever, and you draw this as the inverse, you're going to get this. Is that a function? Clearly not, because it fails vertical line test, right? But now, if I only keep one of these, which is my continuous piece in a piecewise continuity, we call it the principal, right? That would give me only one of these squiggles. And that squiggle is continuous, so now I have inverse function. So this stack of these ones is just an inverse. This one only is inverse function. And we can deal with functions in calculus. We integrate, differentiate, we do all of those things. When you stack 5,000 of them, it's not a function, we can't use it in calculus. So there are these, subtle things that are there, and our knowledge of continuity, domain, and where you chop, right, would help. Another example would be our beloved x squared. When you draw an inverse, it's this. Is it a function? No, it's not a function. It's not a function. It fails vertical line test. Sorry, right? But if you chop the domain, then it becomes just that. And guess that's your root x, right? And this is your x squared, but it has to be on 0 to infinity so that we can over here have the inverse function. So restrictive domain and all of this kind of stuff, right? Sometimes you can, as you can see, you have to chop up the continuous function on the entire domain to create inverse function on the other end. So this is where the pre-calc 1 a little bit peeks in, says hello, and then just leaves. And that's it. That's the continuity. I hope you're not disappointed. Continuity at the point leads to global continuity, which is if the function is continuous at every point, it's globally continuous. 3 ways to get the function to be discontinuous. And then the theorem on list of continuous functions. Theorem on combinations and composition of continuous functions are continuous. And now piecewise continuity, which tells us that even a discontinuous functions will have pieces at the domain that are continuous, which we might need to use in certain cases and certain situations, which is mostly what actually happens. And that's it. Bye. Yes?
Question on the graph. What's the positive values of x squared graph? The brackets versus the parentheses?
Include and not include. So it.
Well, 1 over x is continuous. Included.
We did not include. We put the parenthesis, right?
Yes, so doesn't that include?
No, does not include. Does not. And the bracket is include, yes. Brackets are include, and this one. That's why infinity will always have this, right?
That's why I was going to get that.
Good. So, and when you have asymptotes, you can't include either, because asymptote is the point where everything. We did talk, when I talked about infinite limits, right? We talked about, we did talk about, right, how if you short circuit your outlet, you get the mini explosion, because the denominator is trying to be 0, and when you divide 110 volts by 0, it shoots to infinity. So infinite current is trying to make infinite temperature over short period of time, release of energy. That's why you get small explosion. when you take the U-shaped wire and stick it inside or the outlet, right? That's what it is. So that works that way. Okay, good, perfect. Yes?
I have a question about the tangent graph. Could you say that it's continuous on all points except x equals n pi, like n pi over 2? Like, would that make sense?
Well, it's piecewise continuous, so we have to exclude the asymptotes. So we would say it's continuous everywhere except that, and then we would write where all the asymptotes are. But as I said, in general, we only care about one of those squiggles.
Okay.
So we don't have to be that specific, but you're 100% right.
Oh.
It's continuous everywhere except at those points. Okay. Yes. So that would be pi over 2 plus minus n pi, where n is 0, 1, 2, 3, going on for infinity, right? So these are the ones that you have to exclude, because that's where the asymptotes are. You can do the same thing for secant and cosecant and cotangent. And those are usually people freak out when they see the graph of secant. It's like, oh, you just remember that it's 1 over cosine and just flip it out. That's I don't see people teaching it this way. I'm not sure why, but your secant graph, secant x, you draw a cosine, right? Just a regular cosine graph. Snake it through, and any time when the cosine hits 0, you draw vertical asymptote, and just take these cups and invert them out. That's all it is. And just get rid of the cosine. What's left is your secant graph. That's the way to draw secant, cosecant, cotangent, all of them. Right? Just flip it out. Just flip it out. So your cosine was in here. That's where your cosine was. So anywhere where the cosine hits the x-axis, you put the vertical asymptote, because secant x is 1 over cosine x, right? So when cosine is hitting x-axis, that means that the cosine has 0 in the denominator. That's why that's where the vertical asymptotes are. And you just take these cups and just flip them out. You get rid of the cosine and you're done. The rest is the secant graph. So now you can practice with the cosecant, which is 1 over sine. You draw a sine, hit all the vertical asymptotes where sine goes to 0, and just flip the cups out. And you're done. So now you see that the secant graph has all of these discontinuities as it goes through. But then you can pick a single one, because you do have an inverse secant function. Clearly you can't inverse this, because it would be infinitely many of these, and they all fail vertical line test, right? So you can only pick a principal and draw that one, which is where the continuity becomes important. Cool? Bye.